So now that you know about torque and you've learned all the stuff from all the other videos, what we're going to focus on is we're going to focus on a specific kind of torque problem, which are problems that have rotational equilibrium. Rotational equilibrium is like the equilibrium we've dealt with in the past. In the past, if something was in linear equilibrium, it meant that it's either moving at a constant velocity or it's not moving at all. Rotational equilibrium means that it's either not spinning or it's at a constant velocity. The big reason for that, though, is similar to why things move with linear equilibrium. In linear equilibrium, it meant that they had no net force. In this one, it means they have a net torque equal to 0. But it's much easier to write it as that the torques that are going clockwise equal the torques that are going counterclockwise. So I have 3 example problems that will help us start building some of our skills in solving these kind of problems. The first one, we have a dad who loves his son very much, and they've gone to play at the park together, like they always do, because he's a good father who spends time with his children. The son gets on the seesaw. He's about 2 meters away from the pivot. And the question is, where should the dad sit? If the dad sits all the way at the same end, he sits on the seat that's 2 meters out, the dad's constantly going to just exert way more torque than the son does. And either the dad's going to get really exhausted because he has to constantly throw himself back up, or the dad's just going to be exerting a lot more force all the time, or the dad just stays on the ground the whole time and the kid begins to cry, but the dad's a good father, so he's not going to do that. Instead, we're going to figure out where he should sit. So we're going to set this up as a torque problem. And torque problems should be set up kind of similar to a free body diagram, in that we're going to start with the point that represents kind of our object. But what we have to do here is we have to be a little bit more clever about how we apply our forces. Because if I just try to apply the force of the dad and the son, we can't see any kind of rotation taking place here. So instead, I'm going to apply the forces at a distance. I'm going to create my lever arms by going out here. And I'm going to say, way out here, this is the son. I'll call him R2, which is 2 meters. And he's applying a force that is 130 newtons. That's the force of his weight, M times G. On the other side, at some smaller distance, it's not to scale, but we know it's smaller. R1, the dad's going to sit, and he's going to apply his greater force of 850 newtons. So from here, we can already start setting up our torque problem. I'm going to say the torques that are going clockwise equal the torques that are going counterclockwise. In fact, I'm going to do it the other way around. Sorry, counterclockwise and clockwise, just so that these ones are on my left side and these ones are on my right. So that would be R1, the lever arm of the dad, times 850 newtons, is equal to the lever arm of the son, that's 2 meters, times the force of the son, 130. So you can see that I have the torques that are going clockwise on the right side and the torques that are going counterclockwise on the left side. So if I just want to solve for R1, I would just divide both sides by 850. That'll cancel that out. And I get 0.9, I wrote it down. No, 0.3. 0.3 meters. Okay, so that's how you do that problem. This one's pretty basic. Just want to get us introduced to kind of the problem solving strategies. Next problem, all right, the dad and the boy are still playing together because only a bad father would take a son to the playground, hop on the seesaw with him, and then be like, all right, peace. But what they're going to do next is now the son wants to see if he can hold his dad up. But the dad knows, of course, he can't hold him up, but he wants to build his son's confidence. So he says, hey, son, I got an idea. You hold up the seesaw, and I'm going to start at the pivot point, and then I'm going to walk towards you. And let's see how far I can get to you before you have to let it go. But you'll totally be holding me because I'm on the seesaw and you're holding up the seesaw. So we already know the boy can't hold more than 400 newtons. And he's standing at this 2 meter long end. So we want to figure out where the farthest the dad's going to get before his son's arms get ripped off. Oops, that makes it look like not a good father. We're just going to figure out the furthest he could stand. So let's set up this problem again. I'm going to identify my pivot point. It's this pivot point right here. And we already know that the son is way out here 2 meters away. That's our lever arm for the son. And he's going to exert a force upwards of 400 newtons. Then the dad's exerting a force downwards at some unknown lever arm. So again, I'm going to call that R1, but we know that the dad's mass is still 850 kilograms, so that's, or sorry, 85 kilograms, so that's 850 newtons. So setting this up again, I'm just going to set the torques going one way equal to the torques going the other way. So I'm just going to say R1 times 850 equals 2, that's the lever arm, times 400. So R1 is just going to be equal to, if I divide both sides by 850. And this one comes out to be around 0.80 meters. Boy, this is fun. Notice here, though, that we have to be really careful about thinking which direction our forces are going. And we have to be really good about identifying our pivot point. Okay, next problem. Father and the son are up to no good now. They've disassembled the tilting board, and they've pulled it off, and they weighed it somehow and found out that it had a mass of 10 kilograms. Then they set it up so that it's on this little support column, and the son wants to see, wants to kind of do the same thing that the dad got to do. So the only thing that's different is now it's 4 meters long because it's from end to end. It's no longer pivoting right in the middle. But that's going to change a couple things. So the first thing that we have to identify, we're trying to figure out how much weight the dad's supporting. But the first thing we have to figure out is we have to figure out where to put the pivot point. And that part's less obvious now because there is no given pivot point. It could pivot at multiple locations. You can imagine that if this end broke, whatever's holding it up, then it would pivot at the dad's hands. We can also imagine that if the dad lifted it up and lowered it, it would pivot right here. And in fact, depending on how you manipulate the system, the pivot point could exist at many different locations. So one key thing to know about rotational equilibrium problems is you can control where the pivot point is, and that will let you solve different types of problems. In this case, I'm going to put my pivot right at the left-hand side. The reason for that is if I draw this out, I'm going to draw a straight line. This is my 4 meters long. I know that the dad is going to be exerting some, we'll call this FDAD force, force of dad. I know that the son is somewhere here, putting his 130 newtons down at that distance there. And there's actually one more force here that I need to be aware of. There's the force and the weight of the board itself. The board itself didn't really matter before because the center of mass of the board was always right over the pivot point. So it wasn't exerting a torque because even though it had a force, it had no lever arm. But now we actually have a force. Oops, that was a little bit too big. We now have a force from the mass of the board itself of 100 newtons. So we have all of those different potential torques, and we even have a torque here, which we can call the force of the support. So you can see that this problem has a lot of forces involved, and we know some of them, but we don't know all of the distances, and we don't know all of the forces. Actually, we do know the distances, I guess. But we don't know two of the forces. So we have to set this up, and we have to figure out where to put our pivot point to make our lives easier. I'm going to put my pivot point right here. If I put my pivot point there, now even though F support exists, it's not creating a torque. And so it made my job easier. If I'd put it on the other side near the dad, that would be the right way to find what the force of the support would be, but it would cancel out the force of the torque caused by the dad, which is part of what we're trying to solve here. Okay, so think about where you're putting your pivot points. But now looking at this, you can see that I have two forces that are going clockwise and one that's going counterclockwise. So I can put together my equilibrium expression where I say my torques going one way equal my torques going the other way. Let's start with the dad. We'll say the dad is 4 meters out. That's his lever arm. We know that he's 4 meters from the pivot point that we just decided. And he's exerting some unknown force that we're trying to find, the FDAD force. Then going the other direction, we have the sun. His lever arm is 0.8 meters from the pivot point, and he has a weight of 130 newtons. Then we know the weight of the board is 100 newtons, but we have to figure out where it's being, the force is being applied. And even though in reality, the force is being applied downwards along the entire length, we can simplify it and imagine that all of that force exists right at the center of mass, which is at the 2-meter mark. So that we can say 2 meters there, and we'll get the same answer as if we distributed the mass out the way it really is. But this is a simplification that gets us the right answer a lot quicker than trying to do a distributed mass like that. So if I want to just figure out what FDAD is, I just have to take this whole right side and divide it by 4. And I believe that FDAD, the force that the dad's applying, is 154 newtons. That's what it was when I calculated earlier. So as long as I didn't make any gross errors, that should be correct. Okay, so that is rotational equilibrium problems in a nutshell, how to set them up, some of the key things to look for, and of course, the idea that you can kind of put the pivot point wherever you like. All right, thanks for watching. This video got a little long, but appreciate you sticking around for it.